Okie dokie. Learning targets. We're doing 2.1 types of chemical bonds. Atoms or ions bond due to interactions between them forming molecules or compounds if you'd like to use the correct terminology. So you're going to be able to explain the periodic trend of electronegativity qualitatively through electronic structure of the atoms, the shell model, and Coulomb's law. Determine whether bonds are nonpolar, polar, or ionic based on electronegativity differences. Draw a dipole moment and assign partial charges to elements in a polar bond. Explain the continuum of bonding and determine the type of bond by examining the properties of the compound. Define metallic bonding, and the valence electrons are delocalized, not associated with any individual atom. All right, so chemical bond. Not always the simplest, easiest thing to define, okay? But we're going to start with forces that hold groups of atoms together that make them function as a unit, okay? These are forces that hold them together so they function as a unit. It's like the smallest unit of compounds. Now, this is more of the why do they form. How do they form versus why do they form? The energy of the aggregate. We're talking about the energy of the group. Aggregate is the group. Energy of the aggregate is lower than if they are separated individually. And recalling from last year, the elements of the periodic table, most of them are not stable on their own. The noble gases are stable. They're the inert ones, typically don't bond with anything for the most part because they have their full valence shell and are stable. But all the other ones on the table, not particularly stable on their own. So, what do they do in order to find stability is they bond with other things. And if you're unstable, you're at a higher energy state. So one of the recurring themes throughout chemistry is that the atoms, the compounds, the different types of matter do what they do to achieve a lower energy state. So bonding occurs because when the bonds form, energy is released. Okay, that puts when they're by themselves, they're at a higher energy state. When they come together and bond, energy is released. That puts them at a lower energy state. And this is, of course, going to be some of the energy that we're going to calculate later on when we get to Unit 6. But forming the unit, functioning as a unit is the bonding. But why is it bonding? Okay, it is bonding because it puts it at a lower energy state, which would be more stable. Now, ionic bonding is one of the major types of bonding. We're going to address ionic bonding in grave detail in 2.2. So we're only going to briefly touch on it here. But ionic bonding, the electrons are transferred and they form ions. So usually an ionic compound or ionic bond is going to be formed between a metal, which forms the cation, gives away the electrons, and the nonmetal, which is going to gain the electrons, become the anion. And because they have oppositely charged particles now, those charges cause the electrostatic attraction. The positive and negative attracts to one another, and now they like get glued together based off of that electrostatic attraction. Now we call that a Coulombic attraction. Positives and negatives attracting one another is a Coulombic attraction. Covalent bonding does not transfer electrons, it shares electrons. Now if we're talking pure covalent bonding too, they share those electrons equally. And that's going to usually be composed of a nonmetal and a nonmetal together. Sometimes nonmetals will covalently bond with the metalloids. Remember, the metalloids are on the staircase. That's going to be boron, silicon, germanium, arsenic, antimony, and tellurium. It's basically the ones that go down the staircase except for aluminum. Aluminum definitely goes in the metallic category. If you have metals that bond with the metalloids, then that usually falls in the ionic category because the electronegativity differences are larger. And if you have a non-metal that bonds with a metalloid, it's going to usually typically fall in the covalent category. But as you know, things are not always black and white here. We have a lot of gray gradient area, especially at the upper level chemistry. So intermediate cases too between the ionic, which is the full transfer, and the equal sharing, which would be the pure covalent. Intermediate cases are going to share electrons but not share them equally. Does anybody remember what that kind of bond that is? Polar covalent bond. Very good. Polar covalent bonds, there's an unequal sharing of electrons between the atoms. Results in a charge separation in the bond, a partial positive and a partial negative side. Then yes, it ultimately creates what we call a dipole. Di meaning two, pole meaning ends, so you have two opposite ends of this molecule. One is partially positive, one is partially negative. Make sure everybody had time to wrap. So now the diagram next, kind of showing you the differences in the bonds here. This is Cl2, diatomic chlorine, as you can see. The way that they draw it is like the electron cloud density is equal around both centers, which would be the nuclei where the protons are located, like right around here, okay? And they share electrons equally between them. Now, you could also say about the covalent, pure covalent too, you could also call it a Coulombic attraction, because technically the protons here in this nucleus, right, are attracting the electrons from the other chlorine, and the protons in this nucleus would be attracting electrons from that side. They attract electrons from that side. So technically it is positives attracting negatives, which falls under that electrostatic attraction. It's just that they're not being transferred, they're just attracting them in, and it pulls the atoms close to one another. The polar covalent bond here, which is showing you HCl, little tiny hydrogen there on the left and the chlorine on the right. The cloud, the way it's drawn, of course, is the electrons are spending more time around, the density is going to be around the chlorine because it's more electronegative than the hydrogen. And as you can see, they use the small delta or lowercase delta notation. That's the partial negative. Here's the partial positive sign. And that fills the polar covalent bond. Once again, you still have those Coulombic attractions between the nuclei and the electrons. It's just that hydrogen doesn't have as much pull on the electrons, so it is still attracted, but it's not attracted equally. Now the ionic bond, the way they draw it is they draw them as two separate, completely different ions here, where the clouds are not overlapping. So no overlapping clouds like that is showing that this is not covalent at all, the full transfer of electrons. Your sodium here, okay, the sodium is given away its electron to the chloride, so it's fully positive, no partial charge. And then the chloride over here has gained the electron and it has a full charge here as well, a -1. And like I said, the clouds aren't overlapping because they're not sharing anything. They're not equally or unequally sharing anything. But the reason why they attract to each other is because the positive attracts the negative on the fully charged particles. And it builds a lattice that way. It becomes a repeating pattern of positive, negative, building the lattice crystal, which we're, like I said, going to get into a lot more detail in a later section about ionic. All right, so here is another example showing you HF, which is a polar molecule. It shows you that, H is bonded to F. The F, of course, gets the partial negative over here because it's more electronegative, and hydrogen gets the partial positive. You can also see in these kind of density clouds, the red side, of course, and here is more of a bubble, so the electrons are spending more time around the fluorine. The other thing included in this graphic, which we'll talk about, are dipole moments, and that's what that red arrow thing is. And the way that it points over here, the arrow part is going to point towards the more electronegative element, and the end where it looks sort of like a cross, which I say is like it's a positive, that's going to be the, on the end near the partial positive side of the molecule. Okay, so similar to what we did when we drew the waters around the ions, we're also going to think of this too as the way that it attracts an electric field. So if we have HF, which has its partial negative and partial positive side, as you can see here, okay, and no electric field is applied to it, they're just kind of facing wherever and floating around, maybe in that container, most likely HF. In this particular case, is going to be a gas, in gaseous form. However, you apply the electric field where you have your positive and your negative side, your plates, then they line up and they face and attract to the plate, of course. So the partial positives are going to attract to the negative plate. The partial negatives are going to attract to the positive plate, and they form this nice polarizing line here. Okay, so your turn now. Going to draw how the water would look if we applied an electric field, and you don't have to draw many. Draw like a couple waters in there, 3, 2 or 3, 4 maybe. Typically too, the waters that they ask you to draw are going to look like this, where it's sort of the Mickey Mouse ears. Okay. And I will tell you also about the diagrams that you see a lot of. Usually in these type of models, the oxygens are going to be red, the hydrogens will be white, carbons are usually black, and the halogens, whether it's chlorine, fluorine, or whatever, are usually green. Nitrogen is usually blue. Okay? So, when you applied the electric field to the water, it should have looked like this, where the hydrogens, these are the partial positive side, would face the negative plate. The partial, oops, not positive, that's going to be a negative. Near the oxygen is going to face the positive plate, just like so. Now, let's talk about bonding. Go back to the octet rule, and of course we all know the prefix oct means 8. The octet rule states that elements gain, lose, or share electrons to attain an electron configuration of the nearest noble gas. Noble gases, like said earlier, are ones that are already stable, do not need to bond with other things already at a lower energy state. Now, most of the atoms will obtain 8 valence electrons in order to reach this noble gas configuration. Have the same number of valence electrons as a noble gas. Just to make sure we're all on the same page, what are valence electrons again? The ones in the outer energy level. The outer energy level is going to always be the S and P's in the electron configurations, but we will go back over that a little bit later on in the year. But you can remember the valence electrons pretty much from their column. Like group 1 has how many valence electrons? 1. Group 2 has 2. Now we skip the transition metal section because they can vary. They are multiple oxidation states. The boron group, how many valence electrons? 3. The carbon group? 4. The nitrogen group has 5. The oxygen group has 6. And the halogen? 7. And the noble gases, except for helium, who has 2. One of the notable exceptions, very good. Few exceptions. Helium is stable with 2. So there are some of the elements at the top of the table that mimic helium and do not take on the 8 valence electrons. So hydrogen obviously is one of the most notable ones that only needs 2 in order to be stable. Now lithium and beryllium, they lose electrons and look like helium. They form ions. Boron, metalloid, can do a couple of different things and has its own kind of system, which we'll get to boron later. But they don't typically follow this 8 valence electron pattern. Yes?
Hydrogen loses an electron. Is it stable?
Hydrogen loses an electron, it's H+, and yes, it's can form an acid and hook itself onto water and then form hydronium and stuff like that. Yes? Okay. So yes, that's why we call, when hydrogen loses its electron, we call it a proton, because it is simply just a proton. Good question. All right, electronegativity. What is electronegativity? Electronegativity is the ability of an atom to attract a shared pair of electrons to itself. So it's really that attractive force power to pull an electron. Fluorine is the most electronegative element on the table. And we're going to talk about why in just a minute by looking at the Bohr models. Oxygen is a close second. Okay? Those two. And you probably know more about the oxygen being highly attractive to things, because what causes most of our corrosion and rusting of metals? Well, because it's very reactive with oxygen. And because oxygen is very electronegative, it's very reactive, and it's going to corrode things and form rust with our metals. Okay? The range of electronegativity values, although you see it on the chart that's in your packet, goes from 4 to 0.7. Now I'm going to already qualify that we kind of stop at cesium. The 7th row of the periodic table has a bunch of radioactive elements that we don't really work with in here. We don't even study any nuclear chemistry for AP. And also a lot of them are ones that have, half-lives of, like not even 5 minutes long. So, and were created synthetically in the lab and all of that. So we don't really go into much with regards to the 7th row of the periodic table, or the 7th period. So just stating that for that purpose there. Now, I like this graphic because it kind of shows you with the bars, and as you can see, it's just a general trend. The general trend is that electronegativity actually should just call it EN. Electronegativity increases as you go up, it increases as you go to the right. Okay? That's the general trend. As you can see, not everything follows the general trend on here. And you should kind of get a good idea of these notable ones up here, because they are the highest on the table. Fluorine and oxygen, chlorine and nitrogen are both 3.0s, and then bromine, is 2.8. That's still pretty decently high. Okay. As you can see here, the alkaline metals, alkaline earth metals on this side, they're very low. The transition metals are a little bit higher. And of course it increases as you go across. Okay. And like I said, there's a section in the middle that kind of doesn't necessarily follow the trend, but it's not like way, except for maybe gold, way out of its normal range here. Now, looking at the electronegativity values, we're going to look at the structure and try to surmise as to why this is the trend that it is. Has to do with Coulomb's law. Coulomb's law is written as a proportion here because in chemistry they don't actually have you calculate anything with the equation. What they want you to do is qualitatively see which of the two factors is making more of a difference with either the bonding or the attraction for the electronegativity trend or anything like that. Because you can explain the trends, the periodic trends with Coulomb's law. You can also explain bonding with Coulomb's law as well. So the one factor it's discussing first is the bottom one here, r squared. R squared, like radius, okay, is a measure of distance, really. So the closer oppositely charged particles are to one another, the stronger the force of attraction is going to be. The second factor here is talking about the numerator, the Q1 and the Q2. Q1 and Q2 are talking about the charges on the particles. And if they're oppositely charged, then you're going to have an attractive force over here. And this is going to be an attractive force. If the charges were the same type of charge, like if it was positive, positive, you could still use this, but instead of it being an attractive force, it would be a repulsive force instead. Now, we don't really, measure the repulsive forces. We're looking more for the attractive forces because we're talking about bonding here. So we're going to use it in terms of attractive forces. So Q1 and Q2 are going to represent positives and negatives. They're going to be oppositely charged. So the greater the number of charges, the stronger the force of the attraction. And usually out of those two, the numerator, the charge, the magnitude of charge has a greater effect than the distance, okay? Usually. Now, let's look at the Bohr models and discuss here. Now, Bohr models don't give us really good depiction of like the quantum, nature of our orbitals, but it does kind of give us a distance-wide kind of structure here. Now, if you remember from atomic structure, like this would be n equals 1, and it only has an s in it. This would be n equals 2, and it has a s and a p sublevel in it. Okay? Then, like chlorine down here, this one would be n equals 3, and that would have an s, a p, and a d in it. Right? These are like the shell model it was talking about in the learning targets. Each principal energy level is the n number, and within the principal energy levels are the sublevels, which are the s, p, d, and f, and within them are the orbitals. Now, if you're looking here at the elements that are all in the same period, you have boron, carbon, nitrogen, oxygen, and fluorine. I did them in order across their period. You can see that they have the same number of energy levels, principal energy levels. They have 2, okay? So basically the distance to the outer valence electrons is going to be approximately the same because they have 2 energy levels from the nucleus in the center to those outer energy levels, which would be n equals 2 for all of those. Okay, that's going to be virtually the same. The difference is, we look at fluorine. Fluorine has 9 protons, 9 positives. And boron over here only has 5 positives. So if you're looking at like Coulomb's law, and not going to like technically calculate it, but if I'm looking at fluorine over here, force of attraction, okay, and I'm like looking at this attractive force for that one particular valence electron right here, okay, that means it's going to be plus 9 multiplied by the minus 1. We're talking about this particular electron over, n equals 2, right? Now, if we're comparing that to our boron over here, this proportion here, I'm going to write it as the proportion. This is going to be 5 positives times the 1 negative if we're talking about like that electron over n equals 2. Which one's going to have a larger numerator? Fluorine has a larger numerator, so its force of attraction is going to be greater. Now, with respect to the size and the magnitude of charge, fluorine has like the highest charge value for the smallest size, so that's why it's the most electronegative element on the table. Does that make sense? Now you look at chlorine, which is also fairly, and remember with boron, what is boron? Boron's only a 2.0, fluorine is a 4.0, okay, highest value. So as you can see, just the difference in the 4 protons makes the huge difference in the electronegativity value. Okay, but if you look here at chlorine, chlorine is down the group, and chlorine has a 3rd energy level. So if we're looking here, chlorine has 17 protons. So it has a lot more protons than fluorine, but it also has more distance. So its proton to its distance ratio here gives it a little less force than fluorine, because chlorine is a 3.0. It's still extremely high, it's just not as high as the proportion from the fluorine to its distance. Okay? So you kind of get the idea of how to use Coulomb's law here, describing the shell structure here with the Bohr models. Yes.
So why did you just take the -1? Are you just like comparing it to like a lone electron?
I'm talking, so when I put it in this equation like this, I'm talking about that you have 9 protons in the nucleus here, right? These are representing the charge of the nucleus, and its attractive force for this particular electron. And that particular electron only has 1 negative charge. So that's what we're talking about there.
Oh.
This attractive force for this electron.
So the Coulombic attraction, you calculate it for 1 electron like at a time?
Yes, it would be calculated that way, although we're not calculating it really. We are just like showing that the numerator for fluorine with everything else in its period is going to be greater, so therefore it's going to have the greatest force of attraction for negative charges out of all of the elements in the second period.
Okay. So does the Coulomb's law like calculate the electronegativity of?
I'm sure it probably plays a role, but we don't go into any kind of scope like that at all. We're not even going to calculate using Coulomb's law, although if you take more advanced physics classes, I'm sure you would eventually get there to be doing that.
Okay.
Question?
Is electronegativity why H bonds are so strong?
Not exactly. The electronegativity difference between the hydrogen and fluorine, or the hydrogen and it's H bond, so it's fluorine, oxygen, and nitrogen. It does create a huge electronegativity difference. So what that does for the hydrogen bonding is you get a bigger dipole, and you have a larger a partial positive and a larger partial negative end. It is not a complete full charge, but it is definitely a stronger partial charge than something that doesn't have such a great electronegativity difference. Does that make sense? Okay. All right, so explaining electronegativity, which also explains all the other trends, mind you, but we will go back over the other trends later. Explaining across a period. You have one of 2 ways you can explain it. You can talk about the effective nuclear charge, which is basically the proton number. Okay? It's basically the proton number in the nucleus. Okay? If you have a higher nuclear charge, effective nuclear charge, it's abbreviated ZEFF, ZEF. Alright? Higher effective nuclear charge means that you have more protons, which means you have a stronger force of attraction. Okay, the other way you can explain it is citing Coulomb's law. But if you go the Coulomb's route, you need to put the little proportion in there, like actually write in the formula. Okay? And you would write that in there too. You would be like, here's Coulomb's law, Q1, Q2 over R squared. You would write that in there and you would say the magnitude of charge for Q1 and Q2 in the numerator is increased, and therefore you get a stronger force of attraction due to larger amounts of proton numbers. So you do have to cite that they have more protons as you go across the period. Now, whether you want to use Coulomb's law or the effective nuclear charge way doesn't really matter. But this explains why, atoms get smaller as you go across. And that also explains why the ionization energy increases because of the stronger force of attraction created by having more protons. Okay? That affects all of the trends. Like I said, we'll go back over those trends later, but this is the same reason for all of them. Now, as you go down the group, it's always the same reason for all of the trends as well. But for electronegativity, we're going to just talk about that today. When you go down a group, you add more principal energy levels. Adding more principal energy levels always creates more distance. More distance means weaker force of attraction. You can cite Coulomb's law. You could also add, although they don't really care about the shielding idea, they don't particularly take into account that as part of your answer. They want you to say more principal energy levels creates more distance and it weakens the force of attraction. Now you could use Coulomb's law and do the R squared part on the bottom, talk about that and say, this is the distance right here, the denominator is getting larger, you divide by a larger number, obviously the force of attraction is going to go down, it's going to decrease, okay? So if you're more of the mathematical person, you might want to just cite Coulomb's law and stick to the numerator denominator thing. That's helpful for the mathematical, logical type people. All right, now your turn. See if you can explain it. All right, if lithium and fluorine react, which one has more attraction for an electron? Obviously it should be fluorine. Fluorine, good. Now, like I said before, you can choose one of two ways to explain it. You can speak about the effective nuclear charge, having more protons, means that's going to have a larger force of attraction for the electron. Lithium having a smaller effective nuclear charge with only the 3 protons, obviously, is going to have less force for attracting the electron. You could also use Coulomb's law, but if you're going to use Coulomb's law, you have to write it out with the F in with the proportion Q1, Q2 over R squared. And you are referring to the magnitude of charge, which is Q1 and Q2 in the numerator. And that obviously, because fluorine has more protons, it has more magnitude of charge. Therefore, it's going to be a larger force of attraction. They do, and you would also have to say that they have about the same distance because they have the same number of principal energy levels. Okay? Now, for fluorine and iodine, this is the down the group kind of trend. Which one out of those has less force of attraction? Iodine has less force of attraction for the electron because as you go down the group, you have more distance from more principal energy levels. You have to say more principal energy levels, you have to say distance creates a weaker force of attraction. And like I said, you can refer to Coulomb's law and talk about the R squared on the bottom if you want to, but these are the key things for explaining this trend and all the others, and they will expect to see these buzzwords and things in there for you to get a point. So let's look at how I explain it. Both have valence electrons in the same principal energy level. The second, but fluorine has a greater number of protons, increasing the ZF, or effective nuclear charge, the attractive force of the nucleus for the electrons. Iodine has more principal energy levels with farther distance and more shielding. Attractive force of the nucleus is weaker than fluorine. You do have to phrase it in terms of the particular one that they are talking about. Like this bottom one, you would not want to be talking about fluorine. You need to talk about iodine. Okay, so make sure you're referencing the actual one it's talking about, not doing like the opposite. Okay, let's talk about our gradient of our different types of bonds here. And these graphics do a good job of showing you the difference between the covalent character and the ionic character. So as covalent character increases, ionic character decreases. As you can see, it's very inversely related up here. Okay. Now, electronegativity differences. What it's based off of? Okay, 0 to large electronegativity difference. Okay. So, closer you get to 0 in electronegativity difference, the more covalent you are. The closer you have a huge electronegativity difference, the more ionic you are. Okay, polar, of course, resides in the middle. Depends on the electronegativity difference, too. This is one of the tables that you might see. And like I said, they're not going to usually make you calculate the electronegativity difference. What they want you to do is qualitatively space it out on the periodic table. Now, most that I've seen really put the 0.4 is, if it's less than 0.4 or equal to 0.4, it's considered to be pure covalent. And that's another reason why I told all of you that anything that has just C's and H's in it, the electronegativity difference between C's and H's is 0.4. And everything that C's and H's only hydrocarbons, remember, they're always considered nonpolar. So here, the pure covalent is also called nonpolar. That would be the nonpolar area as well. Now 0.4 to 1.8 on this particular scale, and some scales say 1.7, some scales say 2.0, but obviously to a larger electronegativity difference. But in between is going to be your polar covalent. However, if your electronegativity difference is only 0.6, you're going to be less polar than something that has an electronegativity difference of 1.2. So the more the electronegativity difference in that range, the more polar you are. It creates a bigger dipole, which is also going to alter and change like the force of the IMFs involved. Okay, as you get more polar, you become more stronger regardless of, so your forces, if they're only dipole-dipole, but you have an electronegativity difference of 0.6, another one has dipole-dipole, but the electronegativity difference is 1.3, the one with the 1.3 difference is going to be stronger dipole-dipole forces. Ionic here, of course, huge electronegativity difference means full transfer of electron. Full transfer of electrons mean you get fully charged. Those fully charged particles are intra-forces now. They are ionic, and they are considered much stronger. This is another graphic, like I said, but as you can see, their scale breaks down a little bit different. This one's 2.0. The other one was 1.8, and like I said, sometimes you'll see it somewhere around there. Really just depends on your source of information. However, they aren't going to have you calculate electronegativity difference. And you're going to see how they ask the question in our next exercise. This graphic also shows the electron density clouds, as you can see, for equally sharing, okay, versus unequally, and electron transfer where they maintain their own clouds. Keep their clouds separate. Their clouds do not blend into one another. Okay? So, this information we're going to now be able to rank different types of bonds based off of their electronegativity differences. So here, arrange the following bonds from most polar to least polar. Now, A, B, and C are separate problems, by the way. They're not, this is not one big, huge multiple choice. So we're going to look at A and do A together. Okay? So, they don't want you to actually sit here and physically calculate this. What you should do, though, is locate, like here's N and F, right here, right? You would locate O and F, so I'll use O and F right here, okay? And the last one is C and F. As you can see, based on the way that they are spaced on the periodic table, you should be able to, rank them in terms of electronegativity difference. So, most polar to least polar. Most polar is going to have the greatest electronegativity difference, whereas least polar is going to be not so much of an electronegativity difference. So out of those three types of bonds, there are NF, OF, and CF. Which one is the most polar? Which one? CF is going to have the greatest difference because they are farther away from each other, right? So yes, CF, this is going to be greatest. Then comes NF, good, because it's now the next has the next largest difference. And then OF actually is only 0.5, doesn't have a huge electronegativity difference. They're right next to each other. Okay? So go ahead and try B and C. See if you can rank them from most polar to least polar. Okay, so let's look at B here. If we're looking at B, we have C to F again. Okay, same row. We have N to O right next to each other, same row. And then we have silicon over here to fluorine. Okay, down a row as well. So if you are comparing C to F and Si to F, Si being in period 3 means it already has like the, greater distance and whatever, so its electronegativity is automatically going to be lower than C. So you can just remember that, because it has an extra principal energy level, that it's already going to have less force because it has that greater distance due to the third energy level, principal energy level in there. So out of those three, as you can see, the one that's the most polar is going to be Si to F. Then comes C to F, and then N to O right next to each other. That's going to be not a very big electronegativity difference. Last one here in the C to Cl obviously is automatically what kind of electronegativity difference? Going to be 0. Okay. Let's look at the boron to chlorine then. Boron to chlorine versus sulfur to chlorine, okay? Which one out of those is going to be the most polar? Boron to chlorine, biggest difference. Then comes the S to Cl, and obviously the Cl to Cl is 0, so that's the least out of those. Alrighty. The greater the electronegativity difference between the atoms, the more polar the bond. All right, more polar the bond. Now, different type of question. Which of the following bonds would be the least polar yet still be considered polar covalent? So, if we're looking through our different bond types up there, there's automatically 2 that I can completely eliminate without question. What's one of them? Okay, I heard them both. O to O definitely can go because that's going to be an automatic 0, pure covalent. And then I also heard MgO. And why MgO should go? It's a metal, non-metal, which we know in general is what ionic bonds are going to be. But if you even looked at the periodic table, magnesium's all the way to the left. So it's going to create a huge electronegativity difference, which is going to put it in the ionic category. Now, least polar yet still be considered polar covalent. So here, then we go to our table. We got to look at the table for the rest. C to O and Si to O, and we have N to O. Okay, so which one of those is going to be the least polar out of those 3? N to O, they're right next to each other, and if you do know the numbers, it's just a difference of 0.5, which is just barely polar. So N to O, of course, being the one closest, they are right next to each other and just slightly polar in that bond. Okay, to be considered polar covalent, unequal sharing still must occur. The bond with the least difference in electronegativity, yet still there's some unequal sharing. That would be N to O. All right, here we go, other way. Most polar without being considered ionic. We can still throw out our two because we know this one's ionic. We know this one's pure covalent or nonpolar completely, right? Pure covalent or nonpolar. Now, which out of those is going to be? Let's look at our table and do our referencing. We have C to O. We have Si to O. And we have N to O. So which one's the most polar without being ionic? Yes, SiO, silicon with oxygen. Very good. Same idea here, and generally to be ionic, the bond needs to be across the table with the metal-non-metal arrangement for ionic. So they need to still be two nonmetals if you're going to be covalent. And there has to be a little bit of difference. So we have to go with the one with the greatest difference based off of the spatial relationship on the periodic table. Question?
Usually, if we have to determine what type of bond it is, should we actually do the calculations to determine whether it's polar or covalent?
If they give you electronegativity values, but for our purposes, like I said, what they're going to ask you on the AP exam, they're not going to give you electronegativity values. They want you to spatially compare them, yes, and rank them.
Okay.
And in all likelihood, these type of questions will be in the multiple choice section.
Okay.
All right. Now, how do we know which side of a polar bond is partially positive and which side is partially negative? Okay. Which one gets the partial positive?
The positive side.
The least electronegative element in the pair, yes, or the least electronegative one showing is the partial positive, but it's not just because it's partially positive, it's because it's based off of being less electronegative than the other element. Okay, less electronegative than the other element. So, if I'm looking here for Si and F out of those two, which one is less electronegative? Silicone. So this one's going to get the partial positive. That means fluorine. Although you should automatically, if you see fluorine, fluorine gets the negative. Fluorine's the most electronegative element on the table. That's just the way it is. All right. Now for Cl and P, phosphorus. Which one gets the partial negative? Cl, good. And the partial positive is going to be the phosphorus. Very good. Like so. Most electronegative element gets the negative partial, and the least electronegative gets the partial positive. All right, dipole moments. Dipole moments. Property of a molecule whose charge distribution can be represented by a center of a positive charge and a center of a negative charge. We use an arrow to represent the dipole moment. Point the arrow towards the negative charge center with the tail of the arrow indicating the positive center of the charge. So, here is our lovely water molecule. And what you can see here, as they draw it in the bent shape that it is, and they gave you the ball and stick model here. And what we're basically doing is putting in the dipole moment to show where the positive side of the molecule is and where the negative side of the molecule is. And the electrons are spending more time over here, okay, over here by our oxygen, and less for each of the hydrogen sides. So this is definitely the partial negative, this is the partial positive side. So your arrow should also point in that direction. So here they individually label each particular atom. So you would draw in your dipole moment towards the oxygen. Don't forget to make it sort of across at the end of the tail there. And dipole moments go in. You could also, if you were drawing it separately, you could draw in For Lewis dot structures, a lot of times what we'll do is draw in multiple dipole moments, like this one's a dipole moment towards the oxygen, this one's a dipole moment towards the oxygen. You could also draw them in that way. But it is pointing, the arrow points towards the side with the more electron density. Okay, and that side is going to be, this end is the negative end. The other sides are positive ends. Now, for carbon dioxide, not sure you remember, but carbon dioxide happens to be a nice linear molecule. It's double bonded. If you drew the Lewis dot structure, it would look like this. And don't worry, we'll go back over drawing later, but that's what it looks like. Okay, so the C to O bond, we look at our periodic table, we know that's going to be enough of an electronegativity difference to be polar. So we do have two dipole moments here, although hard to see. We have one going that way towards the oxygen, one going this way towards the oxygen. Because the C to O bond, I think C is 2.5, oxygen is 3.5. If you were to calculate the difference is 1.0, which puts it right in the middle of polar covalent. Not that you would need to do that, but the C to O bond is polar. They point towards the ends, towards the oxygen, as you can see here too. Electron density is being pulled to both ends over here, and the carbon in the middle, you know, is just kind of in the middle. When you have the dipole moments do that, go away from the central atom like that, they basically cancel each other out, and neither end of the molecule has actually got a partial charge on it. So, no net dipole moment, because the dipoles are canceling here. That makes carbon dioxide non-polar. And we used to say it's based off of the symmetry. Well, the reason why the symmetry thing works is because the dipole moments are canceling out. They cancel out because they're pulling away from the central atom, going to the other directions, and we do not have any side of the molecule that has a partial charge to it, rendering it non-polar. Okay? Now, for example, we have chloromethane and tetrachloromethane here. And what you can see here, this little mu thing, which sometimes is used for micro and sometimes used for friction in physics, but here, the little mu symbol means dipole moment. And it's telling you that the chloromethane has a dipole moment measured at 1.87. And sometimes they give you dipole moment data in a table for molecules. Here's tetrachloromethane, where all of the ligands around the carbon here, all of the outside atoms, happen to be chlorine. So as you can see, all of the dipole moments would cancel out, right? They'd all go away from the carbon and go out towards the chlorines. So all the dipole moments end up canceling. So this ends up being a nonpolar molecule, and the dipole moment is 0. So it gives you a little idea here with the electron density, and here we have one directional dipole goes this way. So this is our partial negative side. This would be our partial positive side. Okay? So in essence, yes, that'll later on affect our intermolecular forces. The nonpolar one will just have London dispersion, whereas this one right here with the dipole moment chloromethane, that one's also going to have dipole-dipole forces. This graphic, although not in your notes, is also just showing you different ones that with different net dipoles, which create, you know, polar molecules, and which ones have no net dipole, which are going to create non-polar molecules. So as you can see, all of the ones that have symmetry, the dipole moments are going to cancel out. The ones that don't are going to have directional dipole moments to one side, where you are going to have a partial negative side and a partial positive side. So this is kind of a little bit here showing you more about dipole moments.